Welcome to this lecture of this course Computer-Aided Power System Analysis. In the last lecture, we have started with the concept of building the bus impedance matrix where there is a mutual impedance present between any two lines. We have shown that if we consider two elements connected between four buses which are also connected with each other through some mutual impedance. So, then we can actually represent this entire circuit by an equivalent current voltage relationship, where these currents are nothing but the bus injected currents at these four buses, and these voltages are nothing but the bus voltages of these four buses, and the connected matrix or rather the connecting matrix connecting this bus injection currents as well as the bus voltage vectors is actually nothing but a 4 cross 4 admittance matrix. From that, we have also shown that the injected current at bus 1 or let us say at bus u can be represented by an equivalent circuit. So, then we will now continue from that part, from that point onwards. So, what we have, that we have already represented in the last class, that we had buses u, v, x and y. Between bus u and v there is an element connected having impedance zc. Between bus x and y there is an element connected having an impedance zd, and these two elements are also interconnected with each other by an equivalent mutual impedance Zm. Iu, Iv, Ix and Iy, those are nothing but the bus injected currents at bus u, Vx and y respectively. Vu, Vv, Vx and Vy are nothing but the bus voltages at these buses u, Vx and y respectively. And we have shown that this bus injection current as well as this bus voltage vector can be interconnected with each other by this 4 cross 4 admittance matrix, and from this admittance matrix we can represent that this current Iu, which is nothing but the injected current at bus u, can be represented by an equivalent circuit as shown here. So, we will also now follow the same procedure for the other three currents. So, we will form 4 different equivalent circuits, and then we will try to form a composite equivalent circuit which will represent this particular matrix relationship. So, now let us do. So, from this relation IV we can write down as minus Yc into Vu plus Yc into Vv. So, minus Yc into Vu plus Yc into Vv minus Ym Vx plus Ym Vy minus Ym Vx plus Ym Vy. All these are complex, I must be careful. So, here also we add and subtract from this expression, we add and subtract Ym Vv and Ym. So, we add Ym Vv and subsequently we also subtract Ym Vv such that this expression remains the same. So, from here we can see that Yc can be written as Vv minus Vu by taking these two terms together, plus Ym Vv minus Vx by taking this term and this term together, minus Ym Vv minus Vy. by taking this term and this term together. So, this is the expression. So, again, so now what we have? So, now we have bus u, bus v, bus x, bus y, and this is bus u, this is v, this is x, this is y. IV is the injected current at bus I, and the first term is VV. So, this is YC, so this is YC, so this is YC. Ym into Vv minus Vx. So, Ym into Vv minus Vx. So, let us see that there is an Ym Ym into Vv minus Vx minus Ym into Vv minus Vy. So, this is minus Ym into Vv minus Vy. So, therefore, this current, injected current, is constituting of this current plus this current plus this current. This first current is Yc into Vv minus Vu, that is this current. The second current is Ym into Vv minus Vx, that is this current, and the third current is minus Ym into Vv minus Vy. So, this is the second equivalent circuit. Let us come to the third. Ix is equal to Ym Vv minus Ym Vu minus Ym Vv. So, let us do Ix is equal to Ym Vu minus Ym Vv plus Yd Vx minus Yd Vy plus Yd Vx minus Yd Vy. These are all complex quantities. As before, we now here from this expression we add and subtract something. We add Vym Vx and subtract Ym Vx. So, from here we get Yd into Vx minus Vy. So, taking these two current, these two term Ym Vx minus Vv taking these two term minus Ym Vx minus Vu. So, again, so then therefore, here also Ix can be represented in terms of these three currents. So, again let us try to derive this equivalent circuit. So, this is U V X Y and the injected current is Ix. Injected current in Ix should be constituting of three currents. One current is Id, second is Vx minus Vv. So, Vx minus Vv, third is Vx minus Vu. So, this current is constituting of this current and this current. This current is this, so this is Yd. So, Yd into Vx minus Vy, that is this this current. This current is Ym, so this is Ym into Vx minus Vv. So the first current is Yd into Vx minus Vy, so this current, so this is this term. Second current is Ym into Vx minus Vv, so this is this term. Vx minus Vv, this is this term, and third term is minus Ym into Vx minus Vu, this is this term. So this is the third equivalent circuit. Let us go to the last equivalent circuit. So my Iy, so minus Ym Vu plus Ym Vv. So Iy minus Ym Vu plus Ym Vv minus Yd Vx plus Yd Vy. So minus Yd Vx plus Yd Vy, all these are complex. So we Ym Vu plus Ym Vv minus Yd Vx plus Yd Vy, and we add and subtract Ym Vy minus Ym Vy, all these are complex. So we take these two terms Yd into Vy minus Vx plus Ym into Vy minus Vu minus Ym. So we have taken, for this we have taken this term and this term, and the last Vy minus Vv. So this term and this term. So again we have got U, V, X, Y, this is Iy, this is X, this is Y, this is U, this is V. Yd into Vy minus Vx, Yd into Vy minus Vx, then Ym into Vy minus Vu, Ym into Vy minus Vu. So here would be another Ym this is Yd, and minus Ym Vy minus Vv. So this is minus Ym minus Ym. So this current, injected current, is equal to this current plus this current plus this current if I apply KCL. So first current is Yd into Vy minus Vx, that is this current. Second current is Ym into Vy minus Vu, this is this current, and third current is minus Ym into Vy minus Vv. So this is this current. So we have got 4 equivalent circuits, and now we have to club them together to get the final equivalent circuit. So let us do that. So what we have is, so final equivalent circuit, so bus U, bus V, let us make a big one, bus X plus bus Y. So this is bus X, this is bus Y, this is V, this is U. Injected current here is Ix, injected current here is Iy, injected current here is Iu, injected current here is IV. Let us go to the first equivalent circuit first, okay, U and V. So between U and V there is an element connected YC. So, between U and V there is an element connected YC. So, this is YC. Then between U and X there is a element called minus Ym, U and X minus Ym. So, this is minus Ym and the third one is between U and Y there is a element Ym, U and Y there is an element M, Ym. So, between U and Y there is an element Ym. So, this is Ym, let us see that it is Ym, Ym. So, so we have put the first circuit in this equivalent circuit. So, let us go to the second one. So, we have put the first one, now let us go to the second one. The second one, between U and V there is one YC is connected. So, between U and V YC is already connected. So, we need not put anything extra here. Then between V and Y there is minus Ym connected. So, V and Y there is minus Ym. So, and then V and X there is Ym. So, V and X there is an Ym. So, V and X there is an Ym. So, we need to this is Ym. So, we have put the second circuit. Let us go to the third circuit corresponding to Ix. For Ix there is an element Yd between X and Y. So, there is an element Yd between X and Y. So, Yd then between X and U there is one minus Ym. Between X and U there is already one, there we have already put minus Ym. So, we do not have to add anything, and between X and V there is one Ym, between X and V there is one Ym, we have already connected that. So, we also do not have to add anything. So, let us go to the last one. Between Y and X there is an Yd, between Y and X there is an Yd, we have already connected them. Between Y and V there is a minus Ym, between Y and V there is one minus Ym, and between Y and U there is one Ym. So, between Y and U there is one Ym. So, then therefore, this is the equivalent circuit. So, this is the complete equivalent circuit of this mutually coupled network. So, now we can see that now these 4 branches, or now this entire equivalent circuit, because they are only consisting of admittances or impedances, so then they can very easily be incorporated into the standard bus admittance matrix procedure without any problem. So, we can possibly make it a little neat. So, let us try to do that, because it is looking very clumsy. So, we can possibly try to make it a little neat. So, to make it a little neat, so we again take, so this is u, this is v, this is x, this is y. So, minus y m between y u and x. So, this is minus y m this is y c, u and v is y c, x and y is y d, y and v is minus y m, and these two need to be, so these two need to be done. So, between u and y there is y m. So, between u and y there is an y m. So, to make it between u and y there is one y m, and between v and x there is another y m. Between v and x there is another y m. This we can put here. So, this is the circuit, and as we have said, I u, I v, I x, I y. So, this is the circuit. So, this is the equivalent circuit. So, then therefore, if I wish to incorporate this into a bus admittance matrix, for example, so then therefore, what I will do, when I am writing down the self admittance term, or rather the diagonal terms, I will simply add this, this and this, and between u and x there would be a term minus of minus y m. So, that is y m. Between u and v there would be a minus y c. Between u and y this term would be minus y m. Similarly, when I would be writing down the row corresponding to v, bus v, essentially the diagonal terms would be consisting of this plus this plus this, and between v and y it would be minus of minus y m, that is y m. Between v and x it would be minus y m, and between v and u it would be minus y c. Similarly, for bus x and bus y. Now, suppose there is only one point. Now, suppose that v and y are the same point, that is both v and y are grounded. So, then therefore, what is happening? So, then what is the case? The case is that I have got bus u, and from bus u there is one impedance which is connected to ground. Then I have got bus let us say x, this is bus u, this is bus x. from there also I have got another impedance connected to ground. So, then therefore, point V and Vy, they are actually the same potential, same point, but they are connected to each other through Zm, and this is Zc, this is Zd, and point V and Y, they are at the same potential. So, then therefore, V and Y, they are actually the same. So, then if they are the same, so then what would be the equivalent circuit? So, then what will happen, because V and Y are the same, so therefore, this will go, this will remain, this and this will come in parallel, as well as this and this will come in parallel. So, then let us draw that. So, then what I have got, bus U, bus X, and there is the common point, this is the common point, so this is bus U, bus X. So, between bus U and bus X, I still have got minus Ym, that we cannot avoid. Between bus U and V, that is the common point, there is Yc. And between U and Y also there is another element, that is Ym, but because V and Y are the same point, so then therefore, Ym is also in parallel with Yc. So, then therefore, we have got another Ym, this is the common, point. Similarly, for bus X, what we will get between bus X and Y is nothing but the common point now, there is Yd. So, there is an Yd, and between bus X and V, which is also nothing but the common point, there is also another element Ym. So, then therefore, there also would be another element Ym. So, this would be in parallel. So, then therefore, in this circuit there are altogether 1, 2, 3, 4, 5 elements. Now, in our previous circuit, how many elements were there? 1, 2, 3, 4, 5, 6. So, you may be wondering what happens to the sixth one. The sixth one has eliminated because V and U, they are the same point. So, then therefore, this term minus Ym is completely gone. So, then therefore, if there is a common point between these two elements which are in turn mutually connected with each other, so then this would be the equivalent circuit. So, in this case, this is let us say Ix and this is Iy, sorry Iu, and this situation is actually more common because you see usually our shunt branches or any branch which is connected to each other, they are usually connected to ground. So, then therefore, this situation is more common, right. But of course, if let us say there are two transmission lines, for example, let us say bus 1, let us say bus I and J, there is one transmission line, and let us say there is bus K and L, there is another transmission line, and these two transmission lines are mutually coupled to each other. So, then of course, in that case this particular circuit will hold good in this case. But however, if this is the case that this is bus I and bus J and then bus L, and there is a transmission line like this and there is a transmission line like this. So, this is bus I, this is bus J, this is bus L, and these two lines are mutually coupled with each other. So, in that case this particular circuit will hold good. There can also be a third possibility that there is a bus I and bus J, and there are two parallel transmission lines between bus I and bus j, and these parallel transmission lines are also mutually coupled with each other, that is we cannot neglect their mutual coupling. So, then therefore, in that case what will happen, even these two will go and all these four will come into parallel to each other. So, that is trivial. So, I am just leaving it for you. So, this is the entire equivalent circuit of any two mutually coupled elements. So, by this we have now finished the topic of formation of bus admittance matrix. Now, with this bus admittance matrix at our disposal, we will now continue our actual analysis of the power system network, which we will do in the next classes. Thank you.